professor of economics at MIT, and has written about so many things over so many years. I'm not going to try to tell you. So even though I shouldn't tell my Whitney anecdote, unless he doesn't want me to, which was when I first started in this field, I was working on causal inference, and I realized there's a difference between causal parameters and not causal parameters, and I knew I'd like to leave everything but the causal parameters unspecified, because I didn't want the null hypothesis to be screwed up because of that. And so I knew economics looked at this stuff more than we did, so I looked at 10 years of econometrica, and I saw that Whitney was the person to talk to. This was back in 1988. So I called him up and left a message. I never heard anything. And then 3 months later, he was at Princeton. I got a call that he was coming. He called me, not knowing me from Adam, having no idea who I was. He said he's coming to Boston. He'd be glad to meet. And as far as I remember it, not only did he come, but he stayed with me for a night or two. I mean, he didn't know me from anywhere. And in a weekend, he just spent the whole time explaining semi-parametrics to me. And I'd never been able to get, and then Andrea Brzezinski and I started writing papers about missing data, because we couldn't write papers about causal inference because it wasn't allowed in those days. 15 straight rejections. And finally, I got a semi-parametric missing data paper into JASA, and then I could write anything once you were in JASA, leader for the field. And the only reason I got that in there, it's not what you know, it's who you know. It turned out that Whitney was a referee, except in those days it was a little different. He didn't take the usual 6 months to review it. He took a year. But so we've worked together a lot since then, and he's always open, kind, and any of you want to call him up and ask him for the weekend, I'm sure he'd do it.
Maybe I should tell the other side of the story. I was at Princeton, which is a wonderful economics department, but there weren't a lot of people doing econometrics. And so it was wonderful to talk to Jamie, and I'm sorry it was so slow on that paper. It's a really good paper, but I don't have to say that, right? You all know that. So anyway, that's been wonderful to know Jamie ever since then. So. Okay, so this is want to look at trying to estimate causal and structural effects, in other words, economic effects for non-separable panel data. This is a co-authored paper with Victor, Ben Diener, and Ying Gao, 2 students, and Jerry Hausman. As an NBR working paper, this is somewhat of an update on that. Okay, so introduction-wise, panel data is great for controlling for unobserved confounding in the language of causal analysis. You can estimate counterfactual objects of interest when you have the confounding as time invariant. And the basic idea is, you get effects from how treatment changes over time as long as the confounding is time invariant. So it sounds like some difference thing going on. That's not the way we're going to estimate things here. That's different. We'll come back to that. The objects of interest that we look at in the paper are average policy or treatment effects, bounds on average welfare effects, the consumer surplus that Max talked about earlier, and effects of taxes on taxable income. In economic models, okay, it's important to allow for confounding when you have prices. There's 2 kinds of reasons. In a market, right, The price is endogenous. The market price is endogenous because you know, as price changes, that represents a change in demand or supply, and you need to account for that. Okay, and price is determined in equilibrium, and so it's endogenous. That's kind of unobserved confounding. Or, in some cases, the prices are choices of the agent. Classic example in public economics is a change in the tax schedule. You know, for many years, people have tried to estimate the effective taxes on how much people work, or in modern public economics, on taxable income. And, you know, you can choose your budget set, in the US at least, right? You used to be able to at least, you know, you could choose to own a house or not. That's a huge source of confounding for trying to estimate the effective taxes. Okay, so so that's something we've applied this to also in another paper I'll mention. Okay, so this talk is actually about using linear methods to do that. I'm not motivated by applied work or anything, but I am actually, and am interested in making it as simple to use as possible. So the basic identifying assumption we're working with here is that there is a fixed effects condition, and this condition is that the conditional distribution of heterogeneity in each time period of the unobserved confounding given regressors does not depend on the time period. Mansky was the first one that I know of to formulate this condition, and he used it to estimate a slope coefficient in a binary choice regression in panel data when the x's were, the regressors were correlated with the individual effect, okay? Panel maximum score. Other folks have used it since then. Bohan-Array's thesis did censored regression in that setting, and it's also been looked at more recently by Graham and Powell for estimating a linear model. I'll come back to that. And then more recently for, again, multinomial choice models by Pecos and Porter. So in economics, where does this condition come from? So this is not really a standard causal condition, although people now are working on it, including Imbens and Athey and a number of others, or Athey and Imbens and a number of others are working on it. Okay, where it comes from, I like to think of it in terms of the economics, which is motivated by economic demand or production models. And the unobserved confounders are preferences or technology. And if you have a short enough time period, maybe it makes sense. That's the motivation for the model to say that preferences and technology are time varying. Now, preferences come in because, for example, in the budget set, the budget set's endogenous, and so you can choose what tax schedule you have. And so that creates confounding, okay? But it's reasonable to expect for, some period of time preferences are about the same, okay? So what we're gonna do is we're gonna use that structure to approximate a smooth non-separable model by a linear model. Okay, so we're going to start out with a very general model. Non-separable, you've got an x, you've got an eta, two things can be correlated. Okay, we're going to put a restriction, this time stationary on the restriction, which is going to allow us to identify and estimate these things. And then we're going to do it in the context of a non-separable model, which is, as far as I know, doesn't get more general than that. Except that we are going to impose some smoothness conditions. Okay, so we show that the assumption that we're going to make allows us to approximate a smooth non-separable model by a linear one with coefficients that do not vary over time. Okay, so it's not about differencing, it's about that the coefficients of a regression don't vary over time. Okay, so that allows you to just estimate the preference effects or whatever you want by a linear regression, individual by individual, okay? We'll show that objects of interest can be estimated by that, averaging nonlinear combinations of individual specific regression coefficients, and we use individual ridge regression to estimate the individual regression coefficients, and then debias the estimate of the object of interest for the ridge regularization. We rely on a large number of time periods, okay, for this, because we're approximating a function, and that approximation depends on having many functions of the variable of interest, okay, or correct functional form, and some of the results depend on that. And we do that for identification, consistency, and inference. One of the virtues of the large T approach is it avoids partial identification. In these general non-separable models, if you have discrete regressors, you have partial identification for these kinds of effects, and we don't want to deal with that. And when we have data where you might not need to, and we also know that what happens is T grows, the identified set shrinks. It can shrink very fast, actually, and I'll come back to that later. Okay, so we're going to rely on large T to do this, and so try and avoid the partial identification issues that come with discrete regressors, okay? Importantly, we also provide some ways of thinking about how to check whether this is a problem in your particular data set. The methods are linear and easy to use in practice, and that's helpful in applied microeconomics. Okay, so panel data, we have two indices, I for individual and T for time period. The outcome variable is YIT, and there's a right-hand side vector of variables XIT. YIT is a function of XIT and unobserved individual heterogeneity, eta IT. And so that's just a general representation of a function, really, that the function actually changes with eta. There's no restriction on the dimension of eta here at all. We're not going to impose that. It's well known, like earlier work on continuous treatment effects, that you can represent those things in terms of this kind of non-separable model. The eta, you can think of it as preferences, you can think about it as counterfactuals, or in other ways. So now commonly, this eta is specified as alpha I VIT, where alpha I is an individual effect and VIT is some time-varying shock of some kind, and we'll come back to that. The functional form of G and the dimension of eta are unknown, and this unobserved heterogeneity, that's where the preferences technology or counterfactuals in the causal model, and as I said before, eta can be infinite dimensional. Okay, so there it is again, that's the model. In the application that we have, this is the share of total expenditure spent on a commodity, and XIT includes price, total expenditure, and time-varying covariance. And I'll describe that a little later. We specify that the function G has an economic structural causal interpretation, that G of X and eta, that's going to be our counterfactual. That's the potential value of the outcome YIT when XIT is equal to X, okay? In a counterfactual world where the regressors take the value of X. So we can write a potential outcome as YITX is G of X and eta IT, and that connects the language of causal analysis with what we would do in economics. That's called a demand function, right? If X is price, it's just in our case, the share changes as X changes, okay? And so it's just movement along a demand function as X is changing. The key challenge is confounding, where XIT and eta IT can be correlated for the reasons I said. prices due to equilibrium conditions or due to individual choices can be correlated with preferences. Okay, so here's the assumption. This is the Mansky assumption. The conditional distribution of eta it given xi does not depend on t. Okay, and that's the assumption we're going to make. There's the model and the assumption. Okay, and as I said, it's from Mansky. Now, when you have a decomposition into an alpha I and bit, this is inherently satisfied for alpha, right? I mean, it's like, it doesn't vary. It's a random variable, it doesn't vary over time, so of course its distribution doesn't change with time, conditional on x. And then you also have a bit. So it's restricting the distribution of bit. Okay, so what about that? What about that? Okay, so in economic demand models, alpha I represents preferences, and so VIT is allowing for some time variation in preferences if you continue and interpret it as preferences, okay? It's including in economics, we sometimes think of this as an idiosyncratic shock, something that's specific to an individual and time period, and you always have those in linear models. Otherwise, they don't fit the data. You would never try and explain a time series of demand choices by individuals where you only had an unobserved alpha, right? Alpha that didn't vary. You just don't fit the data. So, and I can say more, I think I'll pass on saying more about that, but you can test that using some economics too. Okay, so the other thing is everybody who's done panel data uses a model like this, nonlinear panel data, including Chamberlain's Handbook of Econometrics chapter, which is logit, right? And so that just in a binary choice setting, the VIT is just the logit error, right? Type 1 extreme value. Even the logit discrete demand model of Perry, Levinson, and Pecos uses such a specification. Again, it's logit. Okay, so this is, you can think of that as just generalizing those two type models to a more general non-parametric, non-separable setting. Okay, so there's the assumption again. Okay, now the other comment I want to make about this is this seems fundamental in a non-parametric setting. If you want, I don't have a theorem. It would be great if there was one. There may be one. I don't have one, but we do have a theorem for the linear model. We'll get to that in a second. Okay, in some sense, what you're trying to do, just intuitively, is you're trying to look at how, you're trying to get the effect of the treatment effect from how x changes over time. Remember, this time stationarity is conditional on x, the whole vector of all the x's in all time periods, and I should have said that before. And so it's allowed for x to change over time, and for those individuals where x changes over time, the eta is not, right? Distribution is not. So that controls confounding from looking over time at the effect of x, okay? In the linear model, it turns out, so that's right, this is a linear model instead of a non-separable one. YIT is theta naught XIT plus eta IT. That assumption is equivalent to saying that YIT is theta naught XIT plus alpha I plus VIT, where VIT is orthogonal to X's at all leads and lags. So, you know, it produces, that's a kind of linear projection version of this assumption. The linear projection of eta IT on the vector of all the X's in all time periods does not depend on T, produces that classic fixed effects type linear model, and alpha I is just a projection. Okay, so it seems fundamental, but it absolutely, you know, that means that, okay, that it is restrictive, and we're really relying on the economic motivation to motivate this for our applications. Okay. Okay, our object of interest that we're going to look at is a difference of two counterfactual outcomes with some multiplied by some weights. Okay, so there it is, theta naught is the expectation of the average over t of some weight HIT plus times g of xit plus minus HIT minus g of xit minus. Second assumption that we'll make is that these weights and the x's are distributed independently of eta it conditioned on xi. Okay, and this condition holds if these variables depend only on xi and the simulated variables that are independent of the data, which covers all of our examples. Okay. So example one, just average effects of alternative treatment, just what looks like an average treatment effect. Now x is continuous, so it'd be in the continuous case. But again, you know, if the x under assumption one, that will be something we can estimate. Example two, this is one of Max's examples also. This is like what you would do to estimate a welfare effect of price changes, like if you were going to impose a tax. For price XIT, a price-induced change delta IT, and UIT distributed as uniformly 0, 1, that's something that you could estimate to measure the welfare effect of the price change, okay? And the UIT, which is a randomly drawn uniform 0, 1, that's doing the integration. So we're doing integration by simulation there. Another example, economics example, is the average of the taxable income elasticity. It turns out that if you make an assumption similar to what public economists have done to estimate the effect of taxes, the log of the tax rate on the log of taxable income, that's a thing that people have looked at. If you make certain assumptions on that, in a panel setting, you can get a panel model, which is correctly specified, where the linear assumption that we're going to use in a minute is correct, okay? Where you just have a constant for the regressors, you have the log of the tax rate for one of the regressors. On the last budget segment, you have the log of the tax rate, the difference of the log of the tax rates for the first and last segment. And that actually controls for a nonlinear budget set, and the panel structure controls for the endogeneity of that. Okay, so why you do nonlinear, estimate the effect of nonlinear taxes with endogenous budget sets. Okay, so it's going to be based, what we do is based on a linear approximation. So what we're going to approximate is, so I'm going to bypass identification of theta naught. We'll come back to that. And first consider estimation. And why can we do that? Time stationarity is like an exclusion restriction. You know, classic simultaneous equations, you need an exclusion restriction, you know, to get an instrument. And you need also a rank condition. And so exclusion restriction, well, that's time stationarity. And so the thing about rank conditions of identification, they can be checked in the data. So the idea is just to take the exclusion restriction, go as far as you can with it, and then when you're done, look for the rank condition, whether it's satisfied or not. So that's what we're going to do for now. Okay, so the linear approximation we approximate the average potential outcome where you average, take the expectation conditioned on the x's in all time periods. Okay.
Checking the rank condition, isn't that like pre-testing for instrument strength, kind of?
Yes, but we're testing whether or not it's, you know, really what you care about here is whether it's 0 or not, right? Whether your rank position. I'll come back to it. Yep. Absolutely. We're not going to do testing. We're going to do something else. So, yeah, good question. Okay, so we're going to consider the average potential outcome. Look at that. And so, you know, that's, we're just going to write that, define that to be h of x and xi, which is the expectation of the average of the potential outcome as a function of x, right? And that's just expectation g of x given a on t, given all the x's. And then the key thing that we're going to rely on is that doesn't depend on t under assumption 1, okay? Okay, so we approximate h of x by as a function of x by a linear combination of a j by 1 known vector. So we're going to do series regression, okay? Okay, we're going to look at a series approximation of that function. Okay, and approximate, you have a constant for the first one, and then you have some other approximating functions. We denote the approximating coefficients from that as beta bar of xi, and we'll just call that beta bar I. And so that's the approximation. H of xi is approximately equal to b of x beta bar of I. Okay, so there it is again, right? And the idea is that for each xi, h of x is a function of x. And so you can just think of this as you take, an approximation which is specific to xi for that function of x. And what's happening is the coefficients are moving that approximation around as xi moves. Okay, now it's known that if h of x is continuously differentiable to high enough order with derivatives with respect to x that are bounded uniformly in xi, okay, major restriction, derivatives bounded uniformly in xi, and x is confined to a Cartesian product of compact intervals, then the approximation error will be small. Okay, with the usual series approximation error holding uniformly over the set of functions. And those theorems like that are called Jackson theorems after this paper, a 1911 paper by Jackson for power series approximation, for univariate power series approximation. And for more recently, there are corresponding results for multivariate approximations for splines and things. Okay, so that's what we're going to rely on. The object of interest has a corresponding approximation. Okay, so let's just take example 1. Theta naught, that's what it is, right? We just do iterated expectations. Take the expectation inside, conditioned on xi. Under our assumption 2, right? Under assumption 2, you can just write that as h of xit plus minus h of xit minus, and then put in a series approximation, okay? And then pull out beta bar. And what you have is the true parameter is approximated by the expectation of some ai prime beta bar I, okay? And ai is known. Okay, it's just a function of the approximating functions and the counterfactual x's, okay? Or the weights go in there too in general. Okay, so there's the approximation again. Known AI. So the average treatment effect is approximated by this linear combination of which come from the functions, the approximating functions, and from the counterfactual values of x, okay? And all objects of interest can be approximated in the same way. The only thing that changes here is that what that AI looks like. Every time you look at a different counterfactual thing of the form we've looked at, counterfactual object, it just changes AI, okay? Okay, so that again motivates an estimator. That motivates an estimator of the form. Remember what theta naught was. Theta naught that we're interested in is right there, right? Okay, that's the theta naught. So what we're going to do, we just saw that it's approximately equal to expectation of ai prime beta bar I. So we're just going to take an average over I, put in the AI, and then estimate something like beta bar I. Now beta bar I don't know how to estimate. Okay, but I know how to estimate something that's like it. Okay, that does well at approximating, and that's just least squares. So, okay, motivates an estimator of that form, and we're going to estimate. We're going to put in a beta I hat. Okay, and it's going to estimate beta I, which is generally not the approximating coefficients. In fact, we're just going to take least squares, right? So what do we mean by least squares? There's the estimator again. AI is known. The beta I that we're going to take just it minimizes the sum of squared error averaged over time of the true h minus the approximation at beta, okay? That really is least squares in this problem, realize that there's nothing random in that. But it does depend on something random, and that's the xi, right? So again, as xi moves around, this coefficient's going to move around, and so it's really, this beta I is just as much a function of xi as the other one is. This is the least squares. That's the coefficients that we're going to estimate. Okay, so what we do is we run a linear regression of the outcome, our approximating functions for each individual, and then use known AI to form the estimator. Assumption 1, the time stationarity condition is completely essential here, right? Because otherwise, the least squares beta would depend on t. And so what happens is because of time stationarity, it doesn't. And so you can run a regression by running a regression for each individual and estimate the beta I, okay? So that's where the hard problem of panel data gets pushed, right? The hard problem is that inherently the things you're interested in depend on the conditional distribution of alpha I given xi. That's a very, very high dimensional problem. We're going to shove it all into the betas. Okay, that's what this does, and that's what this does. Okay. We approximate this non-separable function by a linear one, and then what we do is we estimate the coefficients of the approximation from running individual specific regressions. Okay. Now, in practice, there could be high multicollinearity in the individual specific ordinary least squares regression. That is the identification problem mentioned earlier. And we're going to just ignore it for now and do ridge. Okay. We'll come back again to the identification. We'll do ridge and then debias the average estimate. We're going to debias our theta hat that we get from ridge regression for the ridge regularization. Okay. So let Qi be the x prime x matrix from regressing, only it's a beta I prime matrix here. It's the right-hand side variables for all the observations 1 to t for running a regression of yit on these approximating functions, okay? And let di be a diagonal matrix which has an identity for the all but the first one, okay, all but the first coefficient where it's 0. And what that does is that frees up the constant to be anything when you run this regression. So we're not regularizing the constant. So this is going to allow for a fixed effect, the standard constant fixed effect that's completely unrestricted, okay? And then that's just ridge regression, time period by time period for individual I, okay? We don't penalize the constants, so unrestricted individual specific constants are present, okay? Yeah, so we could construct an estimator following what we were talking about, just by taking the sample average over individuals of AI, which is known, times our beta I hat. But that estimator is biased by ridge regularization, so we debias it. Okay, and here's the debiased estimator, okay? Oh, sorry, that's the ridge one. I changed it to theta tilde, okay? And this happens to debias, and I'll describe what we mean by that in just a second. Okay, so let Wi be Qi plus lambda, that's the ridge regularization constant, times this identity for, except for the upper left element where it's 0. Okay, and that's the debiased ridge estimator. Okay, okay, so very nice computationally, right? Once you pick the B's and the J's, you just run linear regressions, ridge regressions individual by individual, okay? And these other things are just sample averages. These other matrices that go into forming this are just sample averages and matrices, and easy to do. And furthermore, the standard error you can get from the delta method, right? So you just take all these sample averages here, apply the delta method. That's the second sample movement across individuals of the influence function that you get from the delta method, okay? All right, so that's the estimator and its estimated standard error. Okay, so how does this debias? So when AI is a unit vector, well, so this first one is just kind of a interesting interpretation of this debiased estimator. When AI is a unit vector, so think of that as estimating the expectation of the thetas, okay? And you have the correct functional form. We need that also. Then it has an empirical Bayes interpretation, the estimator does. What it is when you have the correct functional form, so that's h of little x is equal to a linear combination of the bx, it's actually equal and not approximately equal. Yit is Gaussian, and each beta I has a Gaussian prior with common mean theta hat, then theta hat is the average of the posterior estimators of the beta i's. Okay, so it's got kind of this self-consistency property. You plug in beta hat as the prior, you continue to get beta hat as the average of then you interpret beta hat as the average of the Bayes estimators for each I, okay? It's one property. Another property is as the ridge regularization factor goes to infinity, the estimator for each slope, the coefficient of non-constant, the non-constant elements of the approximating vector converges to standard fixed effects, okay? So as lambda 0, you get this least squares individual by individual. As lambda goes to infinity, from the debiased estimator, what you get is standard fixed effects. Okay, so that's a nice way of comparing results. You know, you can look at the slope you might be interested, like the taxable income elasticity, and look what happens as lambda changes to see whether allowing for varying beta matters for the empirical results. Okay, so that's an example of that that's useful. When the functional form is correct, and again, you know, h is equal to a linear combination of b's, and beta hat is the average of the slope, then beta hat's unbiased when all slopes do not vary with t. So there's no ridge bias if you don't have any beta variation, okay? If the functional form is correct and qi is non-singular for every I, then as you'd expect, the bias of theta hat goes to 0 as lambda goes to 0. And then the example of one non-constant regressor is sort of interesting. So let's suppose you have bx is 1 and just one other function of b2 of x, and the functional form is correct. Then for sigma hat I squared equal to the sample variance of the b's over all time periods, the expectation of theta 2 hat, the slope coefficient, right, this is again ridge and debias it, okay, take the resulting slope coefficient that you get, is a weighted average of the true slope coefficients where the weights look like that. They're the variance of the regressor over time divided by lambda plus the variance of the regressor over time. So it's a weighted average of individual slopes with more weight given to observations where identification is stronger, right? As sigma squared goes up, this thing, the weight approaches 1, right? Okay, and notice that the weight is 0 if there's no variation. So you don't get anything. Beta I doesn't show up at all, or theta 2I doesn't show up at all if it's not identified, okay, in this way. Something like that would have to happen, right? Because if it's not identified, we're not going to be able to tell. Okay. All right. Not be able to tell what the true beta is. Okay, so what about this ignoring the identification thing? Well, first of all, let me say a couple words about identification. They're not in the current version of the paper. But you can, with continuous x's, like suppose you have one continuous x, you can easily come up with conditions that are sufficient for identification of certain things. Like suppose that, I'll give you a brief verbal description of this. Suppose that the xi, okay, conditional on any value of the fixed effect, the alpha I, or the eta I, let's say this is where eta bit is iad, so we don't have to worry about it and independent of everything, but the alpha I can be correlated with the x's. Suppose that conditional on any value of alpha I, the distribution of x has a density bounded away from 0 by a uniform bound on the unit interval, okay? Then all of these effects will be identified for any xit plus and xit minus that also have a density bounded away from 0 uniformly on the unit interval, okay? And what happens is as alpha varies, the density of x stays bounded away from 0, and so as you look at these second moment matrices, we can do orthogonal polynomials, and you'll get a second moment matrix that has expectation bounded away from 0 conditioned on xi. Okay, it's not actually, that's not quite right, but what will happen is conditional on alpha I. That's true. Sorry, conditional on alpha I. That's true. So that's an example where you get identification. Okay, that goes away if x is discrete, because then what happens? Let's just take the case of 1x. It's binary. Think of treatment effect. Think of a treatment of some kind, and you're trying to estimate the average treatment effect. Then what happens? You sometimes get all zeros or all ones, and for those individuals where the x's are all zeros for all time periods or all ones, the treatment effect's not identified, right? Okay, but what happens, and this is from the earlier paper, what happens is that the probability of that goes to 0. The rate at which it goes to 0 is a little bit delicate, but if you were to assume, for example, for any alpha I, the probability of 0 and the probability of 1, right, is let's say the probability of 0 and the probability of 1, conditional on alpha I, is bounded away from 0 uniformly over alpha I, then you're fine. And in fact, what happens is the identified set, as t grows, shrinks exponentially fast, faster than any power of j. Okay, so that allows us to do the theory and allow for discrete x's in the theory because we're going to make assumptions which are like that, so that the identified set shrinks faster than square root of t, actually. Faster than what really matters for us, because we're averaging over n is square root of n. So that's what we do in section 6 of the paper. Okay. Any questions anybody wants to ask? It's okay. I needed a pause, so. Yes.
So you're getting like root n plus root t, right?
It's for what we're doing it's root n actually. So what happens is it would become, if beta I were actually constant, it changes, and so we're underlying this as an assumption that that's not happening. Yeah, it changes actually if you do this and you actually have the beta is all the same, the rate changes on this, just the coefficient estimate. That is Professor Lianju Su from Tsinghua has a nice paper on that. Yeah, so we're assuming that doesn't happen actually. It's implicit.
Actually, related to that point, my intuition would be that the omega I should be t times sigma hat squared divided by lambda plus t times sigma hat squared. Which would get you to that.
Yeah, it's possible that I don't have the t multiplying or dividing.
So that kind of then gets to the point where you get consistency once once the t gets large, because the regularization becomes unimportant.
That's, oh, I see. No, it's, I think this is the right way to think about it in terms of normalizing. You have to have lambda go to 0, otherwise you still have bias. So even in the limit, you get bias, even if all of these things, so lambda has to go to 0 for this thing not to be biased, okay? Right, that was property D, right? If the functional form is correct and Qi is non-singular for every I, the bias of theta hat goes to 0 as lambda goes to 0. So you need lambda to go to 0 to get rid of the bias. Is that what you were asking?
I mean, yeah, I guess it's just the scale of the exponent.
Yeah, it's the scale. No. So the Qi I defined was, it's actually, the Qi I defined, so if you look back, it had a t in it. Yeah, it had a t in it. Okay, so here's one approach. I think we're going to change this, but one of the things that happens is if it's correctly specified, one approach to the identification, figuring out whether you have a problem in a particular application. Okay, so with problem with identification. So expectation of theta hat given the xi, or x1 through xn, all the x's in all time periods looks like that. Okay, and the interesting thing about it is it's just got the only effect Qi has on this is through a bar I. So it's actually identified, right? You have AI, so you compute what a bar I is, and a bar just includes this regularization in it, and the debiasing for the regularization, okay? So this AI bar will tend to differ from AI depending on the closeness of Qi to non-singularity. As lambda, let me just go through this. So just arguing sort of intuitively what's going on, this vector is close to the first unit vector, and hence AI bar is close to what it is, AI times WI, okay? And that's kind of the limit of what you get as lambda goes to 0, okay? So it's close to, like, AI bar is like WI prime times AI. Okay, so that thing this is really AI bar right here. Okay, well, as lambda goes to 0, that converges to the projection of AI in the orthogonal complement to Qi, the second moment matrix of the regressors. And so, looking at this can tell you something about how far from identification you are. Right? If Q were 0, the orthogonal complement is everything. So if the null space, right, is everything, the orthogonal complement is 0, so that goes to 0. Okay, as lambda goes to infinity. Okay. Otherwise, it's more complicated. If beta I were, let's see, if beta I were an element of the orthogonal complement of Qi, then you get identification, actually, of AI beta I, okay, from this. So what this is doing is, what this debiasing, the ridge is doing is regularizing the AI in such a way that you still estimate an identified effect with AI bar if beta I is identified, actually. Okay, and more generally, it's regularizing AI. So the point of that is you can tell by comparing the AI bar and the AI, they're both observable. They're both observable. They come from observable things, and so you compare those to check for how bad identification is for a set of observations. And so we do that across all observations, okay? Now this is what we use in the example, but I don't think it's quite the right thing, so we're gonna change it. Anyway, application to consumer demand, okay? So let's see. So what we have is we have scanner data from 2010 to 2014, and we're just gonna look at estimating average consumer surplus, equivalent variation for price change, okay? Okay, so what we use these upper and lower bounds and average equivalent variation for non-separable demand, which is what we have from an earlier paper, and it allows for zero quantity choice. The time stationary, let me skip that. Okay. Skip that too. And demand outcome is expenditure share on a group of goods with a price index for the group. So that's another source of endogeneity, actually, is the price index. Okay. Okay, it's from the Nielsen scanner data. Okay. And it's the share specification is a classic demand specification. We model 15 good types, soda, milk, and others. And we use these, follow Berta, Harding, and Hausman in a couple of demand papers, panel demand papers about this. Not going to talk about that. Oops. And, sorry. Yeah, this is the data, 3,396 households. For those years, so that's 60 months, and we use monthly data, we model monthly expenditure, right, and there's the price index we use for the good, and, okay, and some stuff about the economics of that separable specification. Okay, and what the specification we use is actually really kind of a mix between non-parametric and a partial linear type specification. Okay, so we're going to allow the price and the total expenditure, the own price and total expenditure to be up to cubic, and look at the effect of changing that on the results. And then, okay, and then estimate these consumer surplus things, the welfare effect of a price change, and we're going to look at a 10% price change in the price of the good, a 10% increase in the price. Okay, and we deal with having zero price change for, hard to get, identifying the price change when you don't purchase anything. Okay, let's see. Okay, we do milk. We look at milk and soda. Okay, those are the two goods we look at. And here's, I'm going to skip that result, and sorry about this, but now, as I have my computer, I can do this. Sorry about this. Let's do this. Okay, so this is this soda welfare, this is, sorry, let's do milk. Upper bounds. Okay, what do you see? You see some numbers, right? And so these are on those are, let me look at milk welfare upper bounds. Look at the bottom table. That's consumer surplus. So that's this dollar measure, dollars per month measure of the effect of a 10% tax. Okay, and the main thing I want to point to is the difference between the linear and cubic is very small. Okay, so this is our sensitivity check on the functional form. We're allowing for a flexible functional form in our own price and in total expenditure, and we don't get very much sensitivity. Okay, and those are the numbers, and then you could use those in principle to assess the effects of raising the price of milk by 10%. Okay, actually have been some proposals to tax milk more. Okay, for various reasons. Okay, so that's what you could use this for. Okay, to do this, and then we did look at, you know, whether the identification is a problem for this. And so this is a graph of the AI relative, the size of the difference of AI and AI bar relative to the sum of those two. So this is normalized to be something that's between 0 and 1. And you see very, very small departure from 0 here. So we don't think identification is a problem, okay, for consumer surplus. For deadweight loss, it's a little bit of a different story. You get over towards 1. So this is just a QQ plot, okay, for plotting this thing, which is between 0 and 1 across all observations, all eye observations, okay? And you don't get much of a departure from 0 here, but here you do. Maybe the last, 2.5% or something of observations, you might have to worry about this. And we should probably go back and re-estimate those and try and estimate some identified effect, because I'm worried that it's probably not identified for some observations. Okay.
Because deadweight loss is primarily about the slope versus consumer blood surplus, about the level of function.
Well, the deadweight loss is to assess the welfare consequences of the taxes, right?
But locally, it's basically a function of the slope, right? And whereas locally, consumer surplus is a function of the...
Yeah, and I think the issue is that what's happening and what we need to deal better with is that, we're going outside the range of the prices they actually have. By saying you take 10% every price, that includes the highest price. And so we're going outside the range of the prices that's actually in the data for every individual, actually. And yet, I think we want to go back and change that for both of these, but here it doesn't seem to even matter much. So, yeah. Okay, so to summarize, give here linear methods for estimating structural and causal effects in non-parametric, non-separable panel data. When you have fixed effects correlated with regressors, de-biased average of individual specific linear combinations of individual ridge regression, and derived properties of the estimators, ways of checking identification, demand application, and then the asymptotic theories in the working paper. Okay, that's it.
But so I won't say I understood it all, but so you said where was the t having to go to infinity? Because you said you got it under some assumptions identification then.
Yeah.
What happened if t didn't go to infinity?
T has to go to infinity if you have any discrete variables at all, I think. I mean, the theory says that as long as the support's the same for all time periods, you can get sequences of those regressors which have just one value, either 0 or 1 in the binary case. And so it actually, I think generically, this kind of effect's not identified for fixed T. But when you look at the identified set, it shrinks incredibly fast. If you have the probability of 0 and 1 bounded away from 0 conditional on every alpha, conditional on all alpha, if that's true, then it shrinks very fast. So, and we've seen that, we've done graphs. In the other paper I cited, we've done graphs to look at, and it does, and we had examples where that wasn't true. Suppose alpha's normal and B's normal, then you don't get that anymore. I mean that's not quite true. Sorry. If the model for X, the binary X is a binary model where you have the individual effects showing up plus some normal error term, then and if the individual effects Gaussian, then it's not true, because then for some values of alpha you get out to the tails, right? So you really have to say, there is a restriction here, but then, okay, so anyway, I don't want to say more, but then it's more complicated. You still get power rates at which the identified set shrinks, power rates with T, but it depends on how big alpha I, variable alpha is relative to VI. So anyway, yeah, that's the issue. Discrete axis, it's partially identified for any t. So the thing that this does for you is you don't have to worry about trying to avoid having to do partial identification. I know it's important, but you know, not for large t, I don't think. Right.
Any other questions?
Follow-up question to James. Why is it difficult to get a convergence rate in terms of t?
Is it difficult to get a convergence rate?
How small the bias when t grows? Why is it difficult to quantify that? I mean, in theory.
Can you let me come closer? Right?
So why it is difficult to get a bias bound in terms of t? How large t is?
It's not that difficult. Actually, if you just have a binary variable, then it's fine. But if you have, you know, continuous and but nobody's worked it out. Actually, there's no known form for that. I mean, you could work it out, but you don't. If you don't have to, why do it? Right? And so for large t, you know, I don't think you have to do it, and we even see some evidence even in this, you know, fairly large dimensional approximation we have. We have 15 goods. We have, what is it, you know, cubic home price and total furniture. You know, you get very little evidence of any non-identification for AI, right? Or at least with a consumer. Yeah, so you don't need even to worry about it. You can do this. So that's the thing. One of the things you can do is just run these regressions, check this thing, and then if it's, you know, if you see there's a problem, then you can go work on it and figure out if you have to do what the bounds are if you really want that. But they're very sharp. I mean, they're very tight. I think, you know, in these cases, you know, you want to help people avoid having to do it. So applied micro people might actually use this, right? Yeah, applied microeconomics.
All right, let's thank Whitney.